So for the last talk of the day, we have Colson, who is going to talk to us a little bit about why when Apple added native support for Linux containers, maybe this wasn't the best of ideas. So round of applause for.
There we go. Hey everyone, it's really great to be back this year at OBTS 8. Really excited to get to share this research with you all. I've been working on it for quite some time, but I've only got 25 minutes here, so let's dive in. This is BYOB, Bring Your Own Blackbox Isolated Defense Evasion on macOS. So my name is Colson Wilhoit. I'm a senior security research engineer over at Elastic Security Labs. I've also been in the Army National Guard for about 10 years in the cyber branch as well. On X, you might know me as DefSec Sentinel. You may know my work from threats like Candy Corn, Joker Spy, Rust Bucket, and others. All right, here's everything we're going to cover today, or try to cover. It's pretty packed. So, like I said, let's jump in. All right, I'd like you all to imagine you're a threat actor who's gained code execution on macOS. What if you could run your second stage payload or post-exploitation job inside a well-known, signed, third-party process that Mac already trusts, one with generally all the privileges you need, that the vast majority of high-value targets use daily, and it provides anonymity against security controls like Gatekeeper, XProtect, telemetry from the endpoint security framework, and advanced endpoint detection and response solutions. Now imagine Apple handing you a native way to reap all those benefits, complete with well-documented APIs within a signed system process. No imagination required. It's here in macOS Tahoe with the new container framework, which we'll discuss here shortly. So what I'm talking about here is a container, obviously, and this technique is something I'm referring to as isolated defense evasion. What most people, when you think of a container security or a container in general, you think of preventing breakouts to the host, but very few consider what if the container itself is the payload. So what exactly is isolated defense evasion? At its core, it's really a post-exploitation technique where attackers leverage containers and their frameworks not as a defensive sandbox or self-contained app, but as an offensive tool to execute and hide their malicious payloads. So what are some of the reasons this technique is so effective and so powerful? Well, first, containers are small and portable. You can smuggle a container image under 150 megabytes, significantly smaller than any script or binary payload would be. They can be incredibly small. Container images are not binaries or scripts. So they're essentially a file system snapshot stored as a compressed archive, which makes them not subject to the checks or scans that a script or binary may be subject to. They are everywhere developers live and engineers. So Docker itself is a trusted part of daily workflows in companies all over the world. I'm sure many of you here use it on a daily basis. So you can find it just about everywhere. And then activity inside a container completely evades Gatekeeper and XProtect because those checks don't apply inside the Linux VMs where these containers run. And then finally here, containerized processes don't traverse Apple's endpoint security framework. Again, unless they touch the host, to EDR, what's going on inside that container is completely invisible. So I want to address two likely questions you probably have up front, or at least some of you may have. I mentioned this technique relies on using Docker, or in the case of Tahoe, container framework, and the container daemon, and having those present first, and the bad guy can't really know that those are there beforehand. I'd say that's true, but in today's world with targeted attacks, you can have a pretty high degree of certainty that one of these frameworks or tools is on their system. It's the likelihood is very high. And if not, you can at the very least use this technique as a stealthy option for once code execution is gained to execute like I said, your second stage payload or post-exploitation job. It can be used to sidestep defenses, gain privileges, and achieve objectives without triggering any alerts. Now, I also talked about using a container as a payload, which means you need some way to get that container image onto the system in the first place, making initial access and some dropper or loader code execution a prereq. I want to talk a little bit more about this in depth here. So let's get into code execution a little bit. I think it's important to pause and talk about this as it relates to using container images as a payload, because I believe it provides a really unique opportunity, different from binaries or scripts, that in my eyes may elevate this even a little further. So first off, our dropper or loader payload responsible for downloading the image and orchestrating its execution really requires no code execution that would be considered inherently malicious by anyone, because all you're doing is using valid APIs and Python or Swift code to do what you're doing. There's nothing that's going to necessarily be inherently flagged by that. Because all our payload really needs to do is download the container image and, like I said, use valid APIs to interact with that Docker or container framework. This provides us the ability to more easily and readily submit our payloads over to Apple to sign and notarize, which will enable us to execute without being hindered by Gatekeeper and Xprotect and without raising alarms from our users. Really good example of this are some of the new information stealer samples like Odyssey that have recently been uncovered that were signed and notarized. They use Swift to download and execute their OSA script payload as opposed to bringing it along with their initial access payload. And so they were able to get those signed. Apple really didn't have a ton of reasons not to sign them or notarize them because the app doesn't really do anything other than connect to the internet and then execute a system binary. These certificates have been revoked since then, by the way. Second benefit that I think makes gaining code execution much easier in this case is delivery via trusted sources. I mean, you can obviously do this with standard payloads too, but we can host our container image on places like Docker Hub or GitHub, which are trusted and used heavily by developers and engineers almost every day, providing a almost guaranteed way of safe delivery. Third benefit is the variety of payload delivery options we have available here due to the nature of the code and what we're doing. Package, disk image, application, to even include script packages. I could even deploy a PyPy package that downloads my container, runs it, cleans it up, etc. And then fourth benefit, and I think arguably the most important in my opinion, is the ability for all of this activity to hide in the noise. Developers and engineers do the exact same things this payload will do: downloading container images, running container images, accessing sensitive files from containers, and more every day, all the time. It's incredibly, incredibly noisy. I can tell you, working for a big search and security company, this stuff is incredibly noisy. I can deploy diagnostic detection rules at scale, and I can see that this stuff happens all the time, and it's really hard to differentiate malicious from normal. So our payload will fly under the radar, blending in with normal activity. And last but not least, I feel the need to mention AI here. Containers are used extremely heavily in the AI ML space right now, so that provides context, a nice context for us to slip in undetected without raising alarms. So MCP servers, clients, models, things of that nature provide a really juicy opportunity for typo squatting, spoofing, etc. So in summary, for initial access and code execution as it pertains to container images, as a payload provides us with a higher degree of certainty compared to most cases, in my opinion, in being able to gain initial access and code execution on a victim's system. Not foolproof, obviously, by any means, but a payload that downloads a container image, loads it, executes it, provides a pretty unique opportunity. All right, let's see this in action now. We're going to look at some concrete proof of concepts I've made, 2 of them to clarify what I've told you, show you what's possible. The first one will target a macOS system pre-Tahoe on the latest version of Sequoia using Docker, and then the second will target a macOS system on the latest version of Tahoe using the container framework. So we'll kind of give you both perspectives there. All right, the containerized payload I've used in these POCs is extremely small, super simple Python script. All it does is create a compressed archive in memory of the mounted host folder's contents. So we're mounting a host folder, so like your keychain, your SSH keys, etc. In this case, it's the user keychain, and we're sending that archive to a remote file hosting provider. So we're exfilling it off the system, cleaning up, and taking everything. So the container simply acts as the payload's protection and executor here. And I'll say the word payload here is extremely generous because the container is super basic, the script is really basic, this is a non-privileged container, and the Python script itself does things which are actually pretty standard for applications or application diagnostic collection. So, you know, malicious is kind of contextual here. But like I said, the first POC is built with Python. It'll abuse Docker's settings and APIs in order to carry out its malicious goals. For those that are not aware, the Docker engine exposes a version to RESTful HTTP API that clients can use to control the Docker daemon, tell it to do various things with your container. It's exposed locally, usually via a Unix domain socket. That might not always be the case if you have the option unchecked in Docker Desktop, but that doesn't matter either. The CLI and libraries like these and others simply wrap these calls and then they speak HTTP to the socket. So that's how that works. Some key facts to note here with this POC. I'm using the DockerPy Python library. Interacts almost entirely with the Docker API, nothing else. The container image is hosted on Docker Hub in a private repo for this testing. I built it to be an information stealer. So steal your, like I said, your secret files, your keychains, SSH keys, whatever, and exfiltrate them. But this payload could do pretty much anything from dropping a file on the host to executing a file, running system recon commands, all of that. It's extremely fast, super, super fast, and produces no user prompts, sidesteps any defenses and controls, and then even cleans up after itself, leaving pretty much no trace it was ever there. Only prereq is that Docker Desktop be installed, doesn't need to be running, socket doesn't even need to be there. We can manipulate all of that and make it how we want it. So here we go. We'll go ahead and play this. And I'll run CSR util to show you that SIP is enabled. Who am I? I'm not root. So we'll do that up front, but let's download and use a container to steal some secrets and exfiltrate them from my machine. So I'll run who am I, go ahead and clear, run the payload here. I output everything that's happening to the screen, and we'll go over this here in just a second. But, and I'll say obviously too, if I wasn't doing all these checks and outputting all this, it'd be even faster than it already is. I think it says like 12 seconds, but hopefully it wasn't too fast of a demo, but that's it. I just pulled that container image, I stole all your secrets, I exfiltrated them, and cleaned up with no trace, all in under 10 seconds. So to break down kind of all this madness here that I did for sanity when I did this, first we're going to check if the Docker daemon is present and running. Like I said, it doesn't need to be. If not, we then check the Docker settings store to see if the default Docker socket is disabled. If it is, we just enable it. We then ensure we can start the Docker daemon without spawning the GUI. That's a big thing. Usually when you open Docker Desktop, it spawns that GUI. We want to turn that off so the user's not aware that Docker Desktop's being used at all. So we do that. We then start Docker Desktop headless, wait for the daemon to become available, prompt it to pull our malicious container image from Docker Hub. We then tell Docker to run our container, mounting the host folders we specified. The container runs, executes the payload, so it grabs everything, sends it out, exits. We validate successful data exfiltration, and then the container is removed along with its image. The Docker settings file is actually reverted back to what it was originally set to, and then I reset the daemon back to where it was originally set, and then we're good. And then I can come log into your cloud or your SSH stuff after the fact. So all of this in seconds without alerting the user. Now, the second POC is built with Swift. It'll leverage Apple's new Container Framework Client APIs in order to carry out its malicious goals. If you weren't aware, in Tahoe, Apple announced this new container framework to provide a native way for developers to utilize containers on macOS. I immediately honed in on that, alongside some other research, and was like, that can be abused. So that's what we'll do here. In order to easily interact with container client APIs, you will need the container CLI installed, which right now you have to do manually, which includes the API server daemon that hosts the XPC service that the API communicates over. You can get the API package from Apple's Container GitHub and download it. So anyone using the container framework will generally have that installed. XPC, for anyone unfamiliar here, it's like RPC on Windows. It's an inter-process communication mechanism, client-server architecture, and the API provides calls we can make to download our image, execute our image, clean it up, do all the things we need to do here. Key facts about this: it's written completely in Swift. It's less than 50 lines of code, interacts almost completely with the Container Framework APIs, performs, again, the same thing, file and exfiltration, same as the last POC, produces no prompts, again, evades defenses, controls, happens way faster than the last POC. Almost a race condition with file access events. A prerequisite for this POC, like I said, is that the container CLI be installed. Technically, though, you could build and link against the container framework itself. It would just, which natively exists on Tahoe, it would just rely on a little more code overhead, and your binary would be a little bigger with some other dependencies, but it is possible, FYI. Another option is, obviously, you could bring the CLI binary along with you, prompt the user for their password to install it, and then do that too. Out of scope for today, though. So here's the second demo. That's it. 2 seconds. Yeah, even quicker, way quicker than the Docker POC. User credentials, everything gone in a matter of seconds, and you have no idea. It's all cleaned up. Like I said, no evidence. SIP enabled, gatekeeper as well. So we'll walk through this real quick. First thing I did was fetch the default kernel for the Linux VM the container runs inside on Mac, supported by the current platform. Then we pull our OCI, which stands for Open Container Initiative Compliant Image, which is the only type of image supported by the framework. We configure our container to mount the host folder we want, so the user keychain, create, run the container, wait for it to exit, remove the container image and image on disk along with its cached image, all of that, and then we're good. We got our stuff. So POC summary here, what I showed you was an extremely simple payload, just a Python script that zipped up a folder and sent it out. Nothing fancy, nothing really, inherently malicious or nasty looking. The real story here is the container. So by wrapping that payload script within a container image, I was able to download, run, and clean it up completely via native APIs, both for Docker and for Swift and the container framework. So no prompts, no alerts, in seconds. That's what makes this technique so incredibly effective. All right, so now that you've seen how it works, let's look at some in the wild evidence of how this technique is being used by threat actors today and red teamers. Surprising to me, when I went to look for, I was like, there's no way I'm the first person to talk about this stuff. But surprisingly, there was like nothing out there except for a very recent blog post around this technique specifically, isolated defense evasion, being used to bypass EDR. It was blogged about recently by a Japanese researcher, goes by the name of TKMRU, and it actually actually turns out his work was based off of my blog, my work. He cited my own BYOB compromise emulation blog from earlier this year. So that's the only evidence I found of anyone talking about doing this. So yeah, the first evidence I saw of this technique in the wild and really realized how powerful it could be was when I was researching what happened with the BYOB compromise. So if you aren't familiar, BYOB's one of the largest cryptocurrency exchanges out there, and hackers, most likely the DPRK Trade Trader Group, stole a record like 1.5 billion worth of ETH from them by compromising their upstream multi-signature wallet provider SafeWallet, and that intrusion actually began on a SafeWallet developer's macOS system. So the initial access application that was used in that case was Python-based, and it presented the user with two execution options, one of which was to run the Python app inside a Docker container. It was testing this option specifically that made me realize how powerful it was when I executed it and I was looking for telemetry, and I was like, uh-oh, there's nothing. There's absolutely nothing. And I was like, that's a problem. So that's kind of what led me down this path. I won't go into all the details regarding the Python application payload, how it works. You can go read my blog on the Elastic Security Labs page if you want, but you can see everything the payload does inside the black box there, represented there. All this code exec, second stage payload execution, credential harvesting, everything can happen and did happen within that container without the threat actor being worried about any of the defenses or controls in place on the system. Recently, Google released their H2 Cloud Threat Horizons report, in which Mandiant discussed recent DPRK campaigns that they'd investigated. Both of the attacks they discuss here involve the use of a container for payload execution, which is something to note. So threat actors are catching on to this technique and using this in the wild, and we should all definitely take note. On the other side of the coin, red teams are starting to talk about this technique as well. Many of you are familiar with Spectre Ops, great company full of really talented engineers, operators, consultants. At their conference SoCon this year, two of their guys, Lance Kane and Craig Wright, gave a great presentation on modern macOS red teaming TTPs. And one of the main techniques they discussed was containerized payloads. So, using containers to shield themselves against the security controls macOS implements and nosy EDRs. So again, it's being utilized out there. It's gaining traction. Go check out the talk on YouTube if you haven't already. It's a really good talk. Now, something to note with the DPRK and the red team examples here are that they are bringing their container payloads along with them as part of initial access, and they rely on building their container on the victim system using an included Docker file as opposed to downloading the pre-built image and then running it programmatically via API like we did. Their containers were also more long-lived than mine, not just running and exiting. So I think it's an important difference to know, and I do think there are some good reasons for these differences that I think we should briefly mention real quick. The lure determines what's normal. So social engineering context, if I'm presenting you with like a coding challenge, the DPRK likes to do this, or help me debug this project, including a Docker file in those for the user to build and using that as your payload safe house makes a lot of sense, right? So it may depend on context on whether or not you do my method or build on host. Payload type and staging needs, that's also something that's important. So whether you're doing multi-stage campaign payloads, that might drive whether you embed build steps or take a more OPSEC clean focused approach. And then target profile, defender posture, this one is kind of common sense, but if you expect your target does not have an EDR in place or, is not going to be much of a threat to you, threat actors are really lazy. They take the path of least resistance, and if they don't think they need to do all the fancy API stealth stuff, building on host might be more up their alley. but also research and development gap. The pre-built image API approach I've shown you today, it's currently obviously way more OPSEC friendly, way more reliable, way quicker. But from what I've seen, and like I said, we didn't see anything initially, so this is worth a grain of salt, but from what I've seen, real operators haven't adopted it yet, but I do think they will because it's extremely effective. So how can we defend against this? Can we detect it? What do we need to do? Let's look at some methods here. Let's tackle the first POC, see how we can defend against threat actor abusing Docker to run their container payload. We'll focus on that modification of the Docker settings file and the abnormal execution of Docker itself here. I wanted to note there are other libraries, so Go, Node.js, there's a bunch of other ones that allow you to interact with the Docker API, and any well-funded threat actor could easily create a library, and it's not hard to interact with that Docker API. So, for those of you that don't know, now you do. Docker Desktop maintains its setting files, its configuration files in one of two places, depending on your macOS version and your Docker version. These settings are actually writable, allowing us to modify any so-called safe settings in Docker, restart Docker in the background to apply our changes. That's what we did with the POCs. So something to be aware of. One of the things you can do there to ensure those safe settings are enabled is implement a tool like Santa by North Pole Security. Allows for file access authorization, could allow you to lock down that Docker settings file and would prevent a threat actor from being able to abuse it in the way we've shown. I work for Elastic, so with a detection rule, I could write a detection rule that notifies me when the settings file is opened or modified by a process that is not a Docker process. And if this rule was implemented as one of our endpoint behavior rules, I could tie a response action to it that kills the process or the responsible process tree that attempts to do this. So that's another option here. We can also create a detection rule looking for the suspicious or abnormal execution of Docker in this case. So 99% of the time when you open Docker Desktop via the GUI, it's double clicking or it's on system start, and that's going to be the launch daemon spawning Docker Desktop. So this is a pretty good indicator. If you see something else like Python or Node or the open binary opening Docker Desktop, pretty good indicator of something strange. I will say, as far as detections go, this can be bypassed if you use an ls open API call or an XPC submit routine, because that will essentially task the launch daemon to spawn this anyway. But still, this is a good detection to have in place, so definitely take note. We can create detections for Docker sensitive file access and outbound network connections to suspicious top-level domains, but like I said earlier, from what I've observed, these activities can be super, super noisy, and they'll need to be evaluated on a case-by-case basis or a baseline of like allowed or normal activity to be effective. Docker generates container logs that can provide really valuable information regarding container images, container execution. Our agent, Elastic, has a data integration that collects those, ships them back to your cluster where you can build detections, but those are really good things to collect. Like I said, provide a lot of valuable information you can glean about what's going on in terms of container activity. OS Query, another fantastic tool, talked about in the last talk, but our agent also has an OS Query integration, so you can run scheduled or live queries from Kibana against your endpoints, and OS Query has a number of helpful Docker tables to pull from where you can get really valuable data. So I want to make this perfectly clear though, to clear this up. In regards to visibility and the real issue here, which makes this technique, again, so powerful and effective, with an EDR or the endpoint security framework events, we can see network connections, inbound, outbound. We can see sensitive file open, modify, rename events, process executions, etc. There's a big but here, but all of these behaviors are happening on behalf of the container by the Docker process, COM Docker backend, and the Apple Framework SPC service, COM virtualization virtual machine, which are signed, trusted platform binaries, and they're really noisy. So Like I said, determining malicious from normal, and the fact that many security products by default filter sign, trusted binaries out anyway, proves a real problem here. So the real power here, that's the real power here, unless you have this activity baselined or locked down, knowing something malicious in this case is nearly impossible. Second POC, built with Swift Container Framework APIs. Primary detection point here is Swift binaries communication with the Container Framework services that happens over XPC. So the endpoint security framework does collect XPC connect events that allow us to see the Swift binary talking to the Container Framework XPC service in order to import our image, run it, clean it up. And if you collect XPC connect events, you can create a detection rule that looks something like this, inspecting for XPC connections from non-Apple binaries to Container Framework XPC services. This activity should be extremely rare and definitely warrants a deep investigation. In this case, we can definitely look for container process sensitive file access and outbound network connections. It'll probably be a lot less noisy than Docker, given the framework's use is going to be pretty low, pretty rare, until it's had time to develop, catch on, become more popular. In short, same here, everything the container does is carried out on the host as com apple virtualization virtual.pid, assigned trusted platform binary. Apple at least includes the PID of the container here, but the same problem exists. So if we had a container ESF event, we could sequence or correlate these actions to container creation, but unfortunately we don't have that yet. So in many, in the ways we can detect container framework API abuse today is super slim, super narrow. Surprisingly, Apple didn't release any new ES events with Tahoe or any events around the container framework at all in general. So I will be submitting a request for those events with Apple to hopefully get those in the future. And in the meantime, like me and my endpoint dev at Elastic will be working to find creative solutions for telemetry around that as well. So to wrap up the defense section, I wanted to provide you with just some high-level defense recommendations here. Baseline your company's container security behaviors and activities. I know that's easier said than done in many cases, but at least have some sort of standard way developers should utilize containers so that you can observe deviations from it at the very least. Gain visibility into container activity. I mentioned OS query, Docker container log collection, collect those if you can. And then implement technical controls around your developers' container workflows. It's very important. So like Santa for file authorization with the Docker settings, restrict permissions, lock down Docker image retrieval, maybe use Docker Business, which provides a little more enhanced security. Things like that can go a long way. And then finally, deploy detection rules and hunt for anomalies. Because like I said, this is a black box, and unless you're looking for this activity, it's going to fly right past you. So let's wrap this up here. In conclusion, this is really why I called this talk Bring Your Own Black Box, because once that payload is running inside that container, defenders are blind. You are blind, and unless you shine a light on it, you're fighting completely in the dark. Containers are a really powerful shield, I think we've proven today, for attackers, and ensuring that many defenses in place on macOS don't see their payload. This technique, while not really having progressed as far as what I've seen to what I've done for you today and shown you, I think it's coming. I think threat actors are catching on, and I wanted the community at large to be aware of this and to have a plan to defend against it. So I do think we'll see more of this in the future as the container framework becomes more prevalent. Key point here, you need to recognize the danger that containers pose as a tool for the adversary that allows them to bypass defenses on macOS, which is a powerful thing. So start treating containers in the frameworks that run them as part of your endpoint attack surface. And I hope you all enjoyed this talk. I will be trying to release a lot of this and a lot more of the technical details, since 25 minutes. Tough to cram all that into a couple blog posts. So stay tuned in the near future for that. But otherwise, thank you.